Proportional hazards models are a class of survival models in statistics. Survival models relate the time that passes before some event occurs to one or more covariates that may be associated with that quantity of time. In a proportional hazards model, the unique effect of a unit increase in a covariate is multiplicative with respect to the hazard rate. For example, taking a drug may halve one's hazard rate for a stroke occurring, or changing the material from which a manufactured component is constructed may double its hazard rate for failure. Other types of survival models, such as accelerated failure time models, do not exhibit proportional hazards. The accelerated failure time model describes a situation where the biological or mechanical life history of an event is accelerated. Introduction. Survival models can be viewed as consisting of two parts. The underlying hazard function, often denoted, describing how the risk of event per time unit changes over time at baseline levels of covariates, and the effect parameters, describing how the hazard varies in response to explanatory covariates. A typical medical example would include covariates such as treatment assignment, as well as patient characteristics such as age at start of study, gender, and the presence of other diseases at start of study, in order to reduce variability and/or control for confounding. The proportional hazards condition states that covariates are multiplicatively related to the hazard. In the simplest case of stationary coefficients, for example, a treatment with a drug may, say, halve a subject's hazard at any given time, while the baseline hazard may vary. Note, however, that this does not double the lifetime of the subject. The precise effect of the covariates on the lifetime depends on the type of course, the covariate is not restricted to binary predictors. In the case of a continuous covariate, it is typically assumed that the hazard responds logarithmically. Each unit increase results in proportional scaling of the hazard. The Cox partial likelihood, shown below, is obtained by using Breslow's estimate of the baseline hazard function, plugging it into the full likelihood and then observing that the result is a product of two factors. The first factor is the partial likelihood shown below, in which the baseline hazard has cancelled out. The second factor is free of the regression coefficients and depends on the data only through the censoring pattern. The effective covariates estimated by any proportional hazards model can thus be reported as hazard ratios. Sir David Cox observed that if the proportional hazards assumption holds, then it is possible to estimate the effect parameter without any consideration of the hazard function. This approach to survival data is called application of the Cox proportional hazards model, sometimes abbreviated to Cox model or to proportional hazards model. However, Cox also noted that biological interpretation of the proportional hazards assumption can be quite tricky. The partial likelihood, let U denote the observed time for subject I, and let Ci be the indicator that the time corresponds to an event. The hazard function for the Cox proportional hazard model has the form: this expression gives the hazard at time t for an individual with covariate vector x. Based on this hazard function, a partial likelihood can be constructed from the datasets as where θj equals exp and x1, xn are the covariate vectors for the n independently sampled individuals in the dataset. The corresponding log partial likelihood is this function can be maximized over beta to produce maximum partial likelihood estimates of the model parameters. The partial score function is in the Hessian matrix of the partial log likelihood is using this score function in Hessian matrix. The partial likelihood can be maximized using the Newton-Raphson algorithm. The inverse of the Hessian matrix, evaluated at the estimate of beta, can be used as an approximate variance covariance matrix for the estimate, and are used to produce approximate standard errors for the regression coefficients. Several approaches have been proposed to handle situations in which there are ties in the time data. Breslow's method describes the approach in which the procedure described above is used unmodified, even when ties are present. An alternative approach that is considered to give better results is Efron's method. Let Ej denote the unique times, let Hj denote the set of indices I such that E equals Tj and Ci equals 1, and let Mj equals Hj. Efron's approach maximizes the following partial likelihood. The corresponding log partial likelihood is the score function as in the Hessian matrices, where note that when Hj is empty, the summands in these expressions are treated as zero. Time-varying predictors and coefficients. Extensions to time-dependent variables, time-dependent strata, and multiple events per subject can be incorporated by the counting process formulation of Anderson and Gill. In addition to allowing time-varying covariates, the Cox model may be generalized to time-varying coefficients as well. That is, the proportional effect of a treatment may vary with time, e.g., a drug may be very effective if administered within 1 month of morbidity, and become less effective as time goes on. The hypothesis of no change with time of the coefficient may then be tested. Details and software are available in Martinussen and Scheik. In this context, it could also be mentioned that it is theoretically possible to specify the effect of covariates by using additive hazards, i.e., specifying. However, care must be taken to restrict to non-negative values if such additive hazards models are used. Perhaps as a result of this complication, such models are seldom seen. Specifying the baseline hazard function. The Cox model may be specialized if a reason exists to assume that the baseline hazard follows a particular form. In this case, the baseline hazard is replaced by a given function. For example, assuming the hazard function to be the Weibull hazard function gives the Weibull proportional hazards model. Incidentally, using the Weibull baseline hazard is the only circumstance under which the model satisfies both the proportional hazards and accelerated failure time models. The generic term parametric proportional hazards models can be used to describe proportional hazards models in which the hazard function is specified. The Cox proportional hazards model is sometimes called a semi-parametric model. By contrast, some authors use the term Cox proportional hazards model even when specifying the underlying hazard function, to acknowledge the debt of the entire field to David Cox. The term Cox regression model is sometimes used to describe the extension of the Cox model to include time-dependent factors. However, this usage is potentially ambiguous since the Cox proportional hazards model can itself be described as a regression model. Relationship to Poisson models. There is a relationship between proportional hazards models and Poisson regression models which is sometimes used to fit approximate proportional hazards models in software for Poisson regression. The usual reason for doing this is that calculation is much quicker. This was more important in the days of slower computers but can still be useful for particularly large datasets or complex problems. Laird and Olivier provide the mathematical details. They note, "We do not assume the Poisson model is true, but simply use it as a device for deriving the likelihood." McCullough and Nelder's book on generalized linear models has a chapter on converting proportional hazards models to generalized linear models under high-dimensional setup. In high dimension, when number of covariates p is large compared to the sample size n, the lasso method is one of the classical model selection strategies. Tibshirana has proposed a lasso procedure for the proportional hazard regression parameter. The lasso estimator of the regression parameter beta is defined as the minimizer of the opposite of the Cox partial log likelihood under an L1 norm type constraint. Recently, there are a few theoretical progresses on this topic.